regarding exercise 4C. Any problems in doing question 3? 4A, 6D, 6F, 6G, H, or question 8? No? Okay, then could you please pass your paper down to the front? Joanne, do you just wake up? You have a mark on your forehead. Oh, 4C. 4B was yesterday already, right? That one all in here. Alright, let's run through the question that we were doing yesterday for question 5. Hope you managed to complete it. In this question, you were given a table. Okay, then in this table is all the sizes and the quantity for the t-shirts, t-shirt sizes and quantity for each man, woman, and child. Okay, so in part I, let me get my markers. We want to write down two matrices such that the elements of their product under matrix multiplication give you the total cost of the t-shirts ordered for the men, women, and children respectively. Okay, so since we want total cost, okay, what do you think will the two matrices be? Okay, so maybe, Katja, what do you think? What are your matrices? The order of this first matrix is?
1 by 4.
Okay, 1 by 4. Alright, so tell me the elements. 1 by 4, oh sorry. Your elements? 15.
13.5.
13.5. 12. And then, okay, then what is your bigger matrix then? Your other matrix?
4 by 2.
It's a 4 by 3. Okay, so what is your 4 by 3 matrix? 220.
240.
Okay.
180.
Okay.
50, 60, 210, 10, 40, 200, 240.
Okay. Okay. How many of you get the same pair of matrices as Katja? Nobody? How many of you are getting the same pair of matrices? No? Joseph, you got things to add? Okay, you got this also. Okay. If not, okay, then what is the other pair that the rest of you actually got? Bernice, could you share what is the other pair that you got?
3 by 4 and 4 by 1.
Okay, so sorry, what was the first one?
3 by
3 by 4. Okay, so your 3 by 4 matrix is?
220.
240. Okay, so it's the other way around. and then the other one is 4 by 1. So it's just this one in a column. Okay, so how many? I guess the rest of you got this. Okay, let's see. This one is a 1 by 4 matrix, and this is a 4 by 1 matrix, 4 by 3 matrix. At the end, we're going to be getting a 1 by 3 matrix. Okay, to come out of it. And if you were to consider the multiplication, we are taking $15 multiplied by 220, which is the extra large size. Then after that, 13.5 times 240 plus 12 times 180 and 10 times 85. So it does seem to make sense that the cost and the sizes are multiplying and adding up for each other, such that we are able to get the total cost for men. Right? Okay. In this question, we want the total cost of t-shirts for the men, women, and children. So it does seem to be able to work out to give you the necessary matrix that you want. While for the other one, we are looking at a 3 by 4 matrix and then a 4 by 1 matrix, such that we are going to have a 3 by 1 matrix at the end. And if you were to look at the matrix multiplication, we are still taking 220 times 15 plus 240 times 13.5 plus 180 times 12 plus 85 times 10. And that will be the total cost for men, okay, for the men's t-shirts. So the multiplications is working, okay, the adding up is also working. So both answers are acceptable, okay. The answer that you should be getting, okay, should have the elements. So in this particular example, if you multiply them, you should be getting these elements. Okay, so this is the 3 by 1 matrix. While if you're getting the 1 by 3 matrix, it will just be the other way around. Okay? Just that maybe usually okay, if given the table, we just keep the table order in the same manner, okay, for the matrix, so that you don't need to really shift things around and then after that have difficulty visualizing the whole question. Okay, but there's nothing wrong in the calculations for these answers. Okay. Next, we look at part 2. Any questions? So I will not go into the full working out. Okay, I hope that you are able to get that. Alright. Next one, part 2. We want to evaluate the matrix product. So the matrix product in this case, it should give you 725, 455, and 500. Do you all get that? Okay. Then the question asks to explain what the elements in the product represent. Okay, let's get 2 people to give me an answer. Maybe Noi, could you share with us how did you go about explaining the elements? Hang on, the total. And children. Okay. Anything else? No. Okay, so this was what Noi gave. Maybe let's grab another person. Dylan, do you write it in the same way? How did you go about phrasing it? Oh, so this same statement, or respectively. Okay. Okay. Did someone else give any different answer? No? Okay. So let's look at the matrix multiplication, how it works. We are actually taking 220 times 1 plus 240 times 1. So essentially, when we're doing our matrix multiplication, we are adding up everything over here. And what we have in this row over here is actually the number of t-shirts, okay, for men. And then this is total number of t-shirts for women and total number of t-shirts for children. Okay, so this explanation that Noi gave, okay, is fairly accurate, okay, in saying that there's total number of shirts, for men, women, and children. Okay, just that maybe to point out that it is according to the arrangement of the element. Maybe it will be best. It will be good if actually you put in the word respectively. Okay, to state clearly which one is for which category. Okay. Then next, part 3. Okay, for part 3, we should be getting this row matrix. Okay, 280, 340, 590, and 470. Are you all able to get that? Okay. So maybe Amanda, could you share with us how did you go about how did you go about explaining this matrix over here? Sorry, the total number of ordered t-shirts. I think the correct grammar is total number of t-shirts ordered, right? Then
sizes XL, L, and S for men, women, children.
XL, L, M, and S. For men, women, and children combined. Okay, let's take a look at this statement. Okay, so the matrix multiplication, we are doing 1 times 220 plus 1 times 50 plus 1 times 10. So we're adding up all this here. Okay, then after that, we're going to be getting a 1 by 4 matrix. So we're simply taking each element, okay, here to be the sum of all the columns. Okay, so looking at the explanation there, it does seem to make sense that it is the total number of t-shirts ordered in the sizes XL, L, M, and S. Do you think it's necessary for us to actually go on saying for men, women, and children combined? Okay, how many of you think it's necessary to write that statement? Who thinks that it is okay if even if you write this? Okay, then who thinks that you will write this? Okay, alright. Personally, looking at it from this point of view, I feel that it is a bit of an excess to say for men, women, and children combined. Yeah, I wouldn't encourage you to write for men, women, and children combined because it's a bit of excess information. That's how I feel. Yeah. Do you all feel the same? Anybody feel the same? Okay. Because you just want to go straight to the point to talk about that each of it is for the sizes XL, L, M, and S. There's no need to tell you to mention about the gender or whether is it for children or not. Okay, so to follow a similar structure to what we agreed on in part 2, maybe we could just erase this and then add on the word respectively. Okay, I think that just by saying total number of t-shirts ordered in those sizes is sufficient already. Okay, because it can't be this number itself. It's clear that it isn't men only or women only or children only. Okay, it is the sum itself, right? And it is explained in total, the word total already. Okay, yes, Joseph. Spell out this. Yeah, actually I would encourage you to also spell this out, okay, rather than to write it out in short form. Since the question actually used the word extra large in full spelling, okay, so extra large, large, medium, and small. Okay. All right. Next, we look at part 4. Oops, it's really there. We want to write down two matrices such that the elements of their product under matrix multiplication will give the total cost of the t-shirts ordered. Okay, hence find the total cost. So what would your matrices be? What will your matrix be, Jaren? Joshua, it'd be great if you could be copying rather than sleeping. Okay. Doesn't mean that you write then you sleep. Close the while. Very good. You might as well close all the way to outside. Yeah. Okay. Jaren, yes. You have 2 matrices. 1 by 3. Okay, 1 by 3, yes. 1, 1, 1. Okay.
The second one is a 3 by 1.
3 by 1. Okay.
9550. 5430.
Yes.
And 5590.
Okay. Alright, so any of you get the same pair of matrix as Jaren? Okay, a few of you. Alright. Xiaoming, could you share what would your option, what would your pair be? 1 by 4. That is? Sorry? This one below, okay. And the other one is 4 by 1. 15. 13.5. 12 and 10. Okay. So let's look at these 2 sets that your friends have given. Okay. In the first one, we have 111 and 9550, 5430, and 5590. This matrix over here is actually the same one that you get from part I, which is the total cost of the t-shirts ordered for the men. Since you're trying to find total cost of the t-shirts ordered, right, we just want to actually add them up together, and then we will be able to get the total cost as per what we want in this question, right? So when we have a 111 matrix with this matrix over here, and we multiply in this manner, since this is a 1 by 3 and this is a 3 by 1, we are going to take 1 to multiply by this, plus 1 times this, plus 1 times this. So that will act as a summing up of all the elements found in this column matrix over here. Okay? And if you were to write it out properly, you should get 20570. For the other option that Xiaoming has given us, okay, we have here in this matrix the one from part 3, which is the total number of t-shirts ordered in XL, L, M, and S. So since we know the total number of t-shirts ordered in the particular size, we just have to take that value to multiply by the cost of that particular size. So by doing this matrix multiplication, which is a 1 by 4 with a 4 by 1, we are also going to get a 1 by 1 matrix where 280 times 15 plus 340 times 13.5 plus this and times this and so on. Okay, so we are also going to get a 1 by 1 matrix. Okay, but I want to remind in your presentation of your working, this is the answer to the first part of the question that asks for the product of the matrix multiplication, or rather the product of the matrices. Question also asks to hence find the total cost. So please do write a concluding statement to say that the total cost is actually $20,570. This itself is not sufficient, okay, to say that it is a total cost, because that is answering the question. This is after all a matrix, it is not a cost value, right? So you need to still represent it out in the proper statement like that. Okay? Alright, so that's all for your chapter 4.4. So with that, that means that we will have homework as well. Okay, exercise 4D. Just 3 questions. Question 3, 4, and 6. Yes. Okay. That shall be due on the first maths lesson. I don't know when will our first maths lesson be, because not sure whether you heard from your form teachers there might be a change in timetable for term 2. Okay, so I'll just put it as due on first math lesson or e-math lesson. Okay, so do check your new timetable when it's released on the school website.
yeah. How will it edit?
Nikki is not here. What happened to her? Okay, thank you. Anybody else on here? Oh, okay, Emily. And nobody else in this one. What does unyeniosis? What does that even mean? Okay. For chapter 5, I also printed worksheet because there is some drawing required and I need the grids. So it might not be that convenient if you were to write onto your notebook. But I printed it out smaller this time. Since don't need to really read graphs, unlike the statistics one. Alright, so in vectors itself, okay, I think some of you have already come across vectors when you do physics. In fact, I believe in your lower sex science, you would have also covered the idea of scalar and vector. So scalar itself is magnitude only, okay. Some quantities that are considered scalar values, that will be your distance and your speed. Vector quantities are actually things that we consider both the magnitude as well as the direction. Okay, so there are things like your displacement and velocity. So how do we actually go about having a magnitude as well as the direction involved when talking about a vector? Magnitude is usually represented by a number. Okay, so it's representative by a value because it's talking about the size. So we will quantify it using a value. Whereas for direction, okay, we use our positive and negative sign, okay, to actually determine the direction. So usually positive is considered the rightward direction and negative is considered the leftward direction. Okay, but since in vectors we are going all sorts of direction, okay, I will talk more about it later on. Okay, so plus and minus is usually for your direction, magnitude are your values. Okay, so a vector quantity can be represented by a line segment. So the convention that we will be using is that the arrow will represent the direction, while the length of the line itself, okay, will be about the magnitude. So the longer it is, means that the bigger this vector quantity, okay, in a pictorial manner, whereas the direction, the arrow will be telling us the direction now, okay. There are a few ways for us to actually represent our vector. So one representation would be this way, okay. Joseph, I believe my screen is up here, not on your desk. Alright, so one representation is where we label the endpoints of the line, so PQ. And then let's say this is maybe 120 meter, maybe this is a displacement vector. Okay, let's imagine this to be representative of 120 meters. So the notation of the vector that we may use is PQ with an arrow on top. Okay, not sure whether this is very clear in your printing because I can't find a vector arrow. Okay, but in writing, we write it in this manner. Okay, so P is the starting point, Q is the ending point. There is a difference in writing PQ versus QP. Okay, QP in the other sense, Q is the starting point, P is the ending point. So that will affect the direction of our arrow. Okay, so they are actually different. So in a moment I will be talking about that also. Yeah. Use double arrow. Usually we use single arrow, we don't use double. Oh, no. Okay. So, okay, Bobby is asking, okay, what if we write PQ and write an arrow on the other side, is it? Okay, we do not write it in this manner to represent QP. Okay, so we always write our arrow from left to right. Okay. Then the notation for magnitude, okay, is that we use these lines, okay, it's actually called the modular sign, okay, to represent magnitude itself. Okay, magnitude refers to the length. So in this particular case, the magnitude is 120. Okay, and there is a unit which is meter. Okay, sometimes it's no unit given. Okay, then we just use the word units. Right. Another representation of a vector itself could be done this way, whereby we also maybe have a line with an arrow to tell us the direction, and then we label it with this letter A. Okay. You notice that the difference between this and this is that there is no start point and end point labeling. Okay, so this is just telling us that this vector itself, of this particular length, this particular direction, we call it a vector A. Right? So you notice that in your textbook or in most books, okay, when they use it in this manner, okay, this letter A is always bold. So when it's a bold letter A, okay, it is actually a vector. If it is not bold, it is a scalar. Okay? So progressively as we cover more, go into details in this chapter, you will notice what do I mean by not bold and scalar. So how then do we write this bold letter A, okay, in writing? Because there's no way for us to go and bold our letters. Okay, so please don't go and thicken up your letter A or whatever letters that you're writing and then try to make it bold. We don't do that. We just write our usual letter, okay, and we put a curly sign at the bottom. Okay, so that will be how we do it in writing. We will not accept if you make many attempts to bold the letter, okay, to emphasize that it is a vector. So that is not accepted. Right? In writing, the symbol accepted will be A with a curly sign at the bottom. Okay? Then usually when it comes to vector, okay, the letters that we use usually are the small letters. We rarely use big letters for vectors, okay, when written in this manner. Then for magnitude itself, we still use the modular sign, okay, to write it in this manner. Okay? So these are some notations that you will come across in this entire chapter. Moving on to the next one, where we are looking at vectors on Cartesian plane. Okay, Cartesian plane is your grid. Okay. The axis here doesn't quite mean anything. Okay, it doesn't tell you coordinates in this case. It is just telling you how to go about counting the square spaces. That's all. Okay. So to describe the vector PQ, we use a column vector. Okay, it looks just like your matrices, right? 2, 4. So in this particular question, okay, I have drawn for you the vector PQ already, okay, and to write it out in numeric form, okay, we have 2, 4 to represent it. How did I get these 2 and 4? We consider the rightward direction as the x component, okay, for the x component. So this is what we call the x component. And the bottom one is your y component. So there is some similarity to your coordinates, okay, the way you write coordinates. Just that there is no fraction line, no comma. Okay, so looking at our diagram, how we got 2 is that starting from P, because it starts at P, if we go in the x direction, that means towards the right, okay, positive, since you're going in the positive direction towards the right, we are going 1, 2 squares before we reach where Q is aligned vertically. Okay? So therefore there are 2 squares up to Q. Okay? Then if you were to be going up, we are going 1, 2, 3, 4, and going upwards is positive y direction. So that's how we got the 4. Okay, so that is what I mean by considering the right and up to be positive for the x component and y component respectively. So therefore, if I were to look at the vector ST over here, okay, starting from S going towards T, I first move to the right. You can consider moving, moving right in this manner. So to reach T, we are looking at 1, 2, 3. So we move right 3 times in the x direction. Then we move down 4 times, okay, in the y direction. And since you're moving down, so the vector will be negative 4. Okay? So what do you think would then be the vector for xy? How do I represent it in column vector? What do you think the answer will be? Answer? Number 2. X component is? We move right how many squares? 1. Y component? Y is 2. Okay? So in case you are confused, so we have X. We move right 1 time, then we move up 2 times. Okay? So left right direction is your X component, up down direction is your Y component. Okay? Then for Mn, what do you think the column vector will be? Alia? Mn. Negative 2 and negative 3. Okay? So from M, you are moving leftwards 2 units and downwards 3 units. So it will be negative 2, negative 3. Okay? Questions? Right? So keep in mind that this is what we call a column vector. Okay? Because there are a lot of terms that are going to be thrown around in vectors itself. Okay? Then now we talk about the magnitude. Okay? The magnitude is actually derived by using a Pythagoras theorem, okay, to find the length of line segment. So let's make use of the vector PQ in this sense. Okay? PQ, if we just ignore, okay, that it is a vector, just by looking at this line alone, the way we consider the length of this line, we are looking at a squared plus b squared. Okay, so 2 squared plus 4 squared, and then we take square root to determine the length of the hypotenuse. So in general, whenever you're given a column vector, so let's say a vector A with the column vector xy, okay, we take the square of the x component plus the square of the y component and then take square root. Alright, so that is how we determine the magnitude of a vector. If x is actually positive, the magnitude of a horizontal vector, okay, so a horizontal vector will be, for example, in this manner, where we only have x component because there is no upwards direction or downwards direction. So with a horizontal vector looking maybe something like that, okay, we are going to be getting this. And if y is actually positive, okay, our column vector over here is representative of a vertical vector that looks also maybe something like that. Okay, and then the magnitude will just simply be the x component only, or the magnitude for a horizontal vertical vector will just be the y component. Okay, but it must always be positive values because it is a magnitude. So magnitudes must be positive values. You just relate it to the idea of length. Okay, so length itself can never be negative. Therefore, it should always be positive. Okay. Then looking at example 1. Given this diagram over here with some vectors, we want to find out the column vector as well as its magnitude. Okay, so let's maybe just do one example, looking at the vector AB. Okay, so the vector AB, what would its column vector be? Joshua? X component is 3, negative 4. You sure? AB then. Okay, so should be negative 3 and 4, yeah? So from A to B, so we move to the left 3 units, move up by 4 units. So left is negative, up is positive. Okay, so negative 3 and 4. Then the magnitude of AB will be taking negative 3 squared plus 4 squared. That will give us 5. Okay, because we're talking about magnitude, it is 5 units. So please write down the word units. Okay. Then for DE, okay, what do you think DE will be in terms of its column vector? Kelly, what do you think? DE. 50. Okay. So it is a horizontal line. It only moves in the x direction. So 5 units. There's no up or down, so 0 for the y component. So DE, actually there's no need for calculation, okay, because the length is just really the whole x direction kind of counting. So it will just be 5 units, but if you really want to use the formula, you will still get 5. Okay. What about for C? Wei Chan, what do you think the column vector for C is going to be? Sorry, say again. Negative 2, and then the y component. Negative 2 also. Is it? Yeah. Oh, sorry, I forgot. Thank you. You must. Sorry, Wei Chan, you said negative 2 also, is it? For the y component? Yeah. Okay, sorry, I forgot this magnitude sign. Okay, the modular sign. So then, the magnitude of the vector C, in this case, it will be negative 2 squared plus negative 2 squared. And we get square root 8. Okay, if you answer in 3SF, we get 2.83 units. Okay, and then for the vector F, what will the column vector be, Jin Yang? Sorry, 0, negative 3. Is it? Okay. So 0 and negative 3 is a vertical vector going down. So 3 units down. So for the magnitude of the vector F, that will be a 0 square plus negative 3 square. It will be 3. Okay. So a reminder that it should be positive number. So even if down here is negative 3, okay, do keep in mind that the magnitude should be a positive 3. Okay. Moving on, about equal vectors. Okay, we have some vectors over here. Okay, some have the same direction, some don't have the same direction. Some in fact have same length. Okay, so we need to be clear about that. So for the vectors A, B, C, they have either the same direction, that's for A and B, or different direction, which is A and C. Okay, so we call them parallel. Okay, so parallel vectors can have the same or different magnitudes. Okay, so they can be of different lengths, right? That will also be considered parallel. So long as you keep in mind how we recognize parallel lines, okay, so they are in the same direction, so that's what we call parallel. Okay, A and B have the same magnitude and direction, so two vectors are equal. Okay, when we write, then we write A equals to B. So A and B itself, both of them same direction, same length. Okay, so therefore they are equal vectors. For A and C, they have the same magnitude, but they actually have different opposite direction. Okay, I want to emphasize on the word opposite. Okay, later on I'll explain in a moment. Okay, so C is actually what we call the negative of vector A. Sorry, I forgot to bold this when I was typing. So this should be O, or actually you can just write a curly sign at the bottom also can. Okay, I will do bolding in printing now. Okay, so we write A to be equals to negative C. Okay, so when it's opposite, they are negative to one another. For A and E, okay, they have different magnitudes but the same direction. We say that they are scalar multiples of each other, so we will explore more of it in our section 5.4. Okay, when we talk about scalar multiples. So just now I was saying about opposite direction. It's not the same as saying different direction. Opposite direction means that, for example, if I'm from here moving out the door, okay, and then another person from the door moving in here, we are moving in opposite direction. Different directions will be in the sense that I'm from here moving towards the door, and then after that, the other direction would be Joshua maybe from here to the other side of the door. Okay, that is what we call different direction. So there is a difference in these two words. Different and opposite, they don't mean the same thing. Okay, you understand the idea? So we got to be very careful about this word that we're using. Okay, sometimes maybe in our usual conversation, we do say, oh, we're going different direction. Okay, but actually what we mean is opposite direction. So in maths, we are going to be particular about this opposite and different ideas. Okay, so for equal vectors, we represent them in column vector form. If you were to represent it in column vector form, we write it in this manner. And that will also mean that the x component are equal, y component are equal as well. Just like how we recognize equal matrices. Okay, next, example 2. So we want to draw the following column vectors on the grid provided. Okay, you will be expected to draw sometimes as well. Okay, for the vectors. So please use a ruler to draw. Okay. So this grid, the axis is only telling you how to go about counting the squares. Okay, so for 4, negative 3, it doesn't matter where we're starting. It doesn't mean that we're going to be at the point 4, negative 3. In fact, there is no negative that I've written up for you. So what we could do is maybe, let's say if I were to start at this point here, since you're going in the x component 4 units, so 1, 2, 3, 4, and then y component negative 3 downwards 1, 2, 3. So my start point is here, end point is here. So therefore, my vector will be this. Direction of the arrow matters. Start point is here, end point is here, so it must be going down like that. So we label it for negative 3. Okay. In drawing, of course, we usually use a pencil. I'm just using a pencil that we can all see on the screen. Okay. So could you just very quickly try to draw part B and part C as well? Okay. Draw out these two vectors. I'll explain a bit on part D. If you not do part D, then you want to go ahead. Are we all done? Okay. Your negative 2, 3 should look something like that. Maybe you might have positioned it in a different part of the grid. That's fine. Okay. For 4.50, we try to estimate half of this square here. Okay, so it should be 4.5. Okay, in the x direction. Then for part D, when we say negative of 0, 1, it is just saying the opposite of it. Okay, so 0, negative 1. Okay, so negative of 0, 1 is actually referring to 0, negative 1. So x component, there's nothing. Y component, we're going down. So negative 1, or rather 0, negative 1 will look like that. Okay. Next, we look at example 3. Two column vectors A and B are such that A is equals to this, B is this. If given the condition that A and B are equal vectors, we want to find the value of x. So just like how equal matrices are like, the x component will have to be equal, y component will have to be equal. So with A to be equals to B, the two column vectors will be equal. So we can end up solving algebraically. So x is equals to 4 and y equals to 4.5. In part 2, write down the negative of A as a column vector. Since we already know the value of x and y, that means that my column vector for A is now 4 plus 2 and 4 minus 4.5. That is our 6 and negative 0.5. And the negative of A, you can use the negative sign and the vector A, so that will be negative 6 and 0.5. Okay, then in part 3, we want to show that the magnitudes of A and B are actually equals to square root 145 over 4. So I already have the vector A. That will mean that the magnitude of vector A is 6 squared plus negative 0.5 squared. And that gives us 145 over 4. So we just calculate the ones inside the square root sign so that we can get the exact value here. For the vector B, using the x and y value that we have found, so that's 10 minus 4 over 4.5 minus 5. And that's 6 and negative 0.5. And that would give us square root 145 over 4 as well. Since actually both the vectors are equal, they are both 6 and negative 0.5. So therefore, yeah, sure. So I'm really lacking of space here. for part B, we are given a different condition. We are given that magnitudes of A and magnitude of B are actually equal, and then we want to express Y in terms of X. So since the magnitude of A is actually equal, so part A and part B are unrelated. Okay? So magnitude of A will be taking X plus 2 squared plus 4 minus Y squared, and then we take square root. Okay? Magnitude of B will be 10 minus X squared plus Y minus 5 squared. So, since magnitude of A and B are equal, that means that square root of X plus 2 squared plus 4 minus Y squared is equals to square root of 10 minus X squared plus Y minus Y squared. Take square on both sides. We have this. So next step will be to expand, simplify, and make Y the subject. So the X squares cancel out, Y squares also cancel out. So Y is equals to 52.5 minus 12X. Okay, and lastly in part 2, explain why the vector A may not be equals to vector B. Having the same magnitude does not tell us that it is going to be the same vector. Okay, reason, or rather, same magnitude does not mean that it is equal vector. Reason is because, okay, when we calculate our magnitude, we always square it and then we take square root. Okay, so if in the case whereby they are actually in different direction, alright, or rather not in different direction, but if they are opposite direction, okay, they can still get the same magnitude. Because negative direction, when once we square it, it becomes positive. Okay, so to explain this, A may not be equal to B because only the magnitudes are equal. But they may have opposite directions. Oh, sorry. Okay, example will be, let's say 0, 3 versus 0, negative 3. Okay, they have opposite directions. Magnitudes are actually the same, but they are not equal vectors. So to conclude, if two vectors are equal, magnitudes will be the same. If magnitudes are equal, the vectors may not be equal. So then continue with this tomorrow. Please remember to bring your worksheet and also a reminder to those that have not yet submitted your files or those who have already submitted, please remember to bring the WA1